Hello, welcome back to Piers Rocks. Today we're bare metal programming the STM32. I'm working on a project that uses the STM32 and requires it to run at extremely high speed, and the code needs to be extremely high performance. Therefore I've opted for bare metal programming the STM32 using a combination of C and assembly. And today we're going to look at how you get the most out of your STM32F103, this board known as the Blue Pill board. We're going to look at the difference between using the internal and the external oscillator. We're going to look at the difference between executing code from flash and from RAM, where the results might surprise you. They did me. And we're also going to look at the different performance of an STM32 clone. So in terms of test setup, I'm going to be using a Raspberry Pi debug probe to program the STM32. I'm going to be using a stock STM32 Blue Pill development board. And I'm going to be using another Blue Pill development board that I have removed the STM32 from and replaced with an FCM32 drop-in replacement part. We're going to be looking at the output of the clocks from these various devices on the trusty Rigol. Seeing as I want to clock the STM32F103 just as fast as I can, a really good place to start is the clock tree diagram in the reference manual for the microcontroller. I should point out that my application, what I'm looking for is it to run as fast as possible from the internal oscillator to reduce component count on my device. The STM32 can be clocked either from its own internal oscillator, which isn't super accurate. It's accurate to within about plus or minus 1%, the datasheet says. You can also clock it from an external oscillator, an external crystal. So for example, the Blue Pill boards tend to come with an 8 MHz crystal on board that replicates the speed of the internal oscillator, which is also 8 MHz. So if we look at this diagram, we can see and this diagram does look quite complicated, but actually it's reasonably straightforward once you've stepped through it logically. We can see the input from the internal oscillator here. That's HSI, stands for the high speed internal oscillator, I believe. External oscillator comes in here, and you don't need to connect this. You only need to connect an external oscillator if you're going to be clocking the device from an external oscillator. Now, you'll notice that the internal oscillator is 8 MHz and the external oscillator is also typically 8 MHz, although it can run from 4 to 16. But the STM32F103 has a maximum clock speed of 72 MHz. The way that clock speed of the Cortex M3 ARM processor is achieved is by using a PLL, a phase locked loop, within the STM32 device that multiplies whatever clock you're using as a source up to the final clock speed that you want to achieve. So we can see that here. We can see that the high-speed internal oscillator can be fed through to the PLL, or we can see that the high-speed oscillator can also be fed through to the PLL. Now there's one really interesting complication here, and that's that when the internal oscillator is fed to the PLL, it is divided by 2. So the 8 MHz reference is divided by 2 to 4 before it goes into the PLL. The HSE is not divided by 2 before it goes into the PLL. You may be able to divide it by 2 if you want to before putting it in the PLL, but you don't have to. Now the PLL has a multiplier which allows it to take the given input clock, so 4 MHz in the internal case, 8 MHz in the external case, and multiply that up from between anywhere from 2 times all the way up to 16 times, and all integer steps are available to you. So with the internal oscillator, you can multiply the 4 MHz input by 16 times maximum and achieve a 64 MHz clock speed. You can actually get closer to 68, and I'll come on later and explain how you can get 68 MHz from the internal oscillator. With the external oscillator coming in at 8 MHz without a divide by 2, then you would select a multiplier of 9 times to multiply that 8 MHz by 9 to achieve the 72 MHz maximum clock speed for the chip. Now, there are additional complications here. There's a few things I'm just going to ignore here. So there's a low speed oscillator down here. I'm just going to ignore that for the purposes of this conversation. What I'm really interested in is the clock speed of the Cortex ARM core itself, and also some of the peripheral buses. In particular, I'm using GPIOs in my application, so I need to understand the speed I can clock the peripheral bus for the GPIOs at. So if we look at the output from the PLL, so we've now got 64 megahertz, or maybe 68 megahertz, or maybe 72 megahertz. That comes into this block here, and you can feed the HSI or the HSE in directly to this block, so you don't have to use the PLL as a source. You can use the 8 megahertz HSI directly, or you can use whatever external oscillator you have as a direct source. You don't need to use the PLL multiplier. So the sys clock, the clock for the ARM core itself on the processor, comes out of this block. So in my examples, this is typically going to be the PLL output. And you can see here it says 72 megahertz maximum. You can clock the STM32 faster than that, although presumably it becomes a little less stable and uses more, generates more heat at that speed. So that's the system clock, and it's whatever comes out of this block here. So if you're using a PLL, it's whatever comes out of the PLL. Now you see there's a whole bunch of other stuff here, and these are essentially peripherals and peripheral buses. In fact, you can see we've also got a USB clock up here and a flash programming interface clock that come off the chain at different points. So there are two peripheral buses on the STM32F103. There's APB1 and APB2. And the GPIOs come off APB2, and there's some other peripherals there. And there's also peripherals like the timers, some of the timers, that run off APB1 bus. Now APB1 has a maximum clock speed of 36 megahertz. If you're clocking your system greater than 36 megahertz, you have to divide the APB1 clock using this prescaler here by 2 to step it down to 36 megahertz or under. With APB2, it can run at 72 megahertz, so you don't need to prescale coming into APB2. You can access the peripherals on APB2 at the full clock speed, 72 megahertz. But there's something else that isn't, I think, indicated by this diagram, and that's that the flash on the STM32F103 cannot respond at 72 megahertz, and you have to introduce wait states for when pulling data off the flash in the CPU, so it'll wait 1 or 2 cycles for the data to come back from the flash. At 72 megahertz, I think it's above 48 megahertz, you have to have 2 wait states. And then lower than that, I think 24 to 48, you need 1 wait state, and then below that you don't need any wait states. So this can delay getting instructions loaded from flash to your processor for execution. When using the RAM, if you're executing code from RAM, you copy it from the flash to RAM at runtime and then execute it from the RAM. The RAM bus operates at the full clock speed, so 72 megahertz if you're running the device at 72 megahertz. But there may be contention on the RAM bus between the RAM and other peripherals that are connected to that bus. The interface between the CPU and the flash is a dedicated bus. So actually there are some circumstances where running from flash can be faster than running from RAM, even if you're running at 72 megahertz with wait states enabled, because the device, the STM32, also supports a pre-fetch buffer for instructions that is in parallel with executing instructions, pulling data in from the flash continually to fill a buffer that the CPU then uses to grab its instructions from to execute. So if you're running very simple code, very predictable code, very small number of instructions, then you can actually end up with faster execution from flash than you do with RAM, even at 72 megahertz. And we'll see that in real life a little bit later on. I said I was programming the STM32 in bare metal. What this means is I am directly accessing the registers for the device to configure it. I'm writing my code at a very low level. Most of it is in C, all of the startup and configuration code is in C, and my main business logic loop, if you like, is written in assembly to provide the highest possible performance. let me show you how I am accessing registers directly. In my include file, I have a whole bunch of addresses defined as hash defines. So these are effectively the location in the STM32F103's address space where the various hardware registers live. And then I have hash defines for masks and for bit positions. Now, you don't need to define all this stuff yourself. There's a low-level library from STM that you can download and use, even for bare metal programming. The reason I've gone ahead and defined this myself is because I really wanted to understand the goriest details under the hood of how you configure and operate the STM32, as well as having written all the code myself to access the device. I also have large quantities of the STM32F103 reference manual printed out to help me understand what the registers actually do and how you go ahead and configure them. So in my main code, I have a couple of functions that are likely redundant. These just reset the clocking and the bus for the GPIOs, set those registers to default values. They should come up to default values when the device comes out of reset. I set up SWD for debugging the device so I can get logging output using RTT. I set up the MCO. MCO is actually a very interesting capability of the STM32, and it allows you to direct one of the various clock sources to GPIO PA8 on the device. So for me, I can use that to examine each of the different sorts of clocks. I can see what the HSI, the internal oscillator, looks like, what the external oscillator, HSE, looks like. I can see what the output of the PLL looks like, and I can see what the system clock is. It will direct whichever of those clocks you like to that pin and allow you to actually hook up to it on your oscilloscope. Obviously, in a real world application, you might actually use this output to clock some other device in your system. There's one caveat here: the GPIOs of the STM32F103 are rated to 50 megahertz frequency maximum, and if you're outputting greater than that, then the pins just aren't rated to operate at that frequency. It does kind of work, and it works better, I think, on the STM32 than the Chinese clone I've got, the FCM32. Just be aware that you're pushing the hardware beyond where it's rated if you turn this on and you're running whatever clock is being output on that line faster than 50 megahertz. I then go in and set up either the HSI, the internal oscillator, or the external oscillator as the source for my PLL. And in the HSI case, I'm actually implementing a little trick. The STM32 has some calibration data burnt into it, which is presumably unique for every STM32, which is set at factory, which the device reads on boot and applies to the internal oscillator to achieve as close as possible to 8 megahertz. There's also a 5-bit HSI trim register that you can use to manually modify the HSI slightly up or downwards, and its default position is in the center, is a value of 16, and you can take it all the way up to 31 or take it all the way down to the value of 0 if you want it to run faster or slower. So you can actually run the 8 megahertz HSI at 8.6 megahertz if you increase that trim to the maximum value. It then gets divided down to 4.3. Then if you PLL multiply that by 16 times, you end up with a frequency of around 68.8 theoretically megahertz coming out of the HSI, which was fed into the PLN. So that's a useful little trick if you want to squeeze out another 6-7% of performance out of the internal oscillator on the STM32. Spoiler, it doesn't work on the FCM32. The calibration value on the FCM32 looks a little bit suspect at 99, and the HSI trim value seems to have no effect whatsoever on the FCM32. So I'm guessing that's just a capability that's not implemented on that clone device. Anyway, after I set up either the HSI or the HSE, the internal or the external oscillator, I then actually go in and configure the PLL, I set up the appropriate multiplier, I say what source I want to use for it, I enable it, and that waits for it to become active. It takes a few cycles for the PLL to generate the right frequency output. At that point, I switch over the MCO to output the PLL. Actually, you can't feed the PLL directly into the MCO, the output pin. You have to feed in PLL divided by 2, but you can still understand what the PLL is running at if you feed in PLL over 2. I configure the bus prescalers. Actually, the only bus that needs prescaling is APP1, which we talked about. I'm dividing that by 2 because I'm running this device at around 70 megahertz. I set up the flash latency to 2 wait states, like we talked about earlier, and I manually configure the prefetch buffer to be on. It is on by default on the device, but just making sure that that is actually on. And you set the bus prescaler and you set the flash wait states before you actually go and set the clock of the system to use the PLL. If you do that afterwards, then you're going to hit some level of instability because you're still going to be pulling code off flash, but you don't have any wait state, so flash isn't going to be providing the data back to the instruction data back to the CPU fast enough. Finally, in all the setup, I then switch over the MCO to output the sysclock, and then I run my routine. And the routine that I'm running is basically a little bit of assembly, which I'll show you in a second, which just toggles PA4 up and high and low just as fast as it can. And that gives us an understanding of, in the real world, what sort of performance we can get out of the STM32. Although because it's quite a small routine, it is simplified, it achieves quite good performance on flash, which you may well not see when running more complex code. Finally, here's my toggle PA4 assembly function. First thing I do is enable clock for the GPIO A bus. You have to enable the clock for any peripheral that you want to use on the STM32. If you don't do that, the peripheral is not enabled. It doesn't draw any power, but it won't do anything. So I initialize that. I then set my pin PA4 as an output pin, which can run at the fastest 50 megahertz frequency. And then I have my assembly code. First thing I do is I just store off a couple of values. These are the 2 values I'm going to write to the BSSR register that's going to actually switch the pin high and low. I preload those into registers so I can access them really quickly within my loop. I then store the value in the BSSR register to make the pin go high. I store the value to make it go low, and then I loop back to the beginning. Actually, I have a macro here which repeats these 2 instructions 100 times. It's essentially like a copy and paste instruction for the compiler. So we don't end up with, we only do this branch every 100 times we've set the pin high and low. That achieves higher performance from the system because we're not actually doing the branch. It does also mean that the stability of the toggle is a little bit unstable because most of the time it is evenly going high and low, high and low, high and low, but every 100 times we have an extra couple of cycles while we branch back to the beginning of the loop. The next thing I think we should do is see some of this in action. Let's see some of this code running. First of all, I'll show you the defines I have set up. So we're going to be using the internal oscillator. We're not going to trim it. We're going to output the system clock on the MCO pin, that's pin A8. We are not going to use the PLL, and well, we're not going to run our main function from RAM, but we're not going to look at the output of that in this example. So what should we see? We're using the internal oscillator, that's 8 megahertz. We're not trimming it, we're not putting it through the PLL, so we should expect to see a clock speed on the oscilloscope of 8 megahertz, give or take. Remember, this is the internal oscillator, which is not as accurate as the external oscillator. So let's flash the device, and we see an output of close to 8 megahertz. My scope thinks it's 7.98. Next, let's look at using the external oscillator. Again, we're not going to use the PLL to multiply it up. So again, we should be seeing around about 8 megahertz, but hopefully closer, given we're actually using an external crystal. So the code's built, it's flashing to the device, and we see, again, still pretty close to 8 megahertz, 7.98. So the external oscillator doesn't appear to be significantly more accurate than the internal oscillator. As the next example, let's switch back to the internal oscillator, but let's trim it up to its maximum value. So we still won't use the PLL, but if this succeeded in trimming it as far as the documentation says it will, and it suggests each step, each bit of trimming should increase the clock speed by 40 megahertz, well, we're adding 15 to the stock value of 16, so that's 15 times 40, which I think is 600 kilohertz. So we should be seeing 8.6 megahertz coming out of the device with this code. I think it'll be a little bit slower than that from experience. So let's flash this. And there we go. We're seeing 8.4 megahertz, which is much more consistent with what I've seen previously by trimming the HSI up. Next, let's see us trimming the HSI oscillator down to its minimum value. We should be seeing around about 7.5, 7.6 megahertz out of the system with this code. There we go, 7.5 megahertz. So the HSI trimming functionality is working as expected. Right, let me introduce you to my little friend at this point. This is my FCM32. It's a standard blue pill board that did have an STM32 on it. I've taken the STM32 off and I've soldered on an FCM32. Sourced from AliExpress, but I'm pretty confident that this is actually an FCM32. And we'll see how the HSI, the internal oscillator, operates on this device. So if we're running the FCM32, let's just start off by enabling the internal oscillator, not trim it at all, not use PLL, and just output it at pin A8. Okay, so we're seeing a clock speed of 8.1 megahertz from this FCM32. I mean, it makes sense that the internal oscillator is a slightly different value on a different manufacturer's device, but you'll notice that the HSI calibration value, this was 41 hex or 47 hex on my STM32. This is now showing as OX99. Now it looks like a very suspicious value to me. I'm not sure that is a real calibration value. Let's try trimming the oscillator upwards to its maximum value and see what happens. Huh, 8.1 megahertz. It's not moved. Let's try trimming it down to its lowest value. Same, 8.1 megahertz. The trimming value has no effect whatsoever on the FCM32. I'll switch back to my STM32. Let's look at using the PLL. So we'll start off with the internal oscillator trimmed at its regular default value. So on this device we were seeing a clock speed of I think 7.9 megahertz thereabouts. We'll use the PLL to multiply half of that by 16 times. So we should be seeing roughly 64 megahertz coming out of the scope this time around. Again, remember that the GPIO this is coming out of is actually only rated for 50 megahertz, so the signal will be a bit degraded, but we should be able to see the frequency of the signal that we're getting. There we go, 63.8 megahertz. At this point, let's trim the HSI just as high as we possibly can, and this will show us the maximum possible clock speed that we can get out of this exact STM32 chip. Again, the internal oscillator on every chip is going to be slightly different, so you'll achieve slightly different clock speeds on your STM32. There we go, we're getting 67.3 megahertz out of it, which is a 5% bump from the standard highest speed of 64 megahertz. Let's switch over to the external clock now, and let's configure the PLL for a 9 times multiplier. So remember, this doesn't multiply HSC divided by 2, it multiplies HSC itself, which is 8 megahertz, and it'll multiply it by 9. So we should see 72 megahertz come out of the system clock this time. Bang on, 72 megahertz, which is what we'd expect, seeing as we're running an external oscillator. Now, rather embarrassingly, I've just realised that when I showed you HSE before not being fed through the PLL, and we were seeing a clock speed of 7.98 megahertz rather than 8.00 megahertz, I never switched the system over to use it to sysclocking from HSE, and sysclock is what we were looking at on the scope. So given we were seeing such high accuracy on the 72 megahertz, I fix the code, I want to rerun that test and check that we are actually seeing 8.0 megahertz coming out of HSE, not through the PLL. There we go, bang on 8 megahertz now, so apologies for that mistake. Now at this point I know you want me to see if I can overclock the system, so let's try a PLL multiplier of 12. 8 times 12 is 96, so we should get 96 megahertz out of the system now. Close, 90 megahertz. There's likely to be some scope inaccuracies at this level, but let's push it all the way. Let's set the PLL to 16. I don't know that my scope can cope with this, but it does appear to be a frequency of 128 megahertz, which is what we'd expect to see. Anyway, I'm going to step this back down to a PLL multiplier of 9, so the maximum rated frequency for this chip. Alright, we're back running at 72 megahertz. Let's have a look at our GPIO toggle function, which should be running in the background, toggling, I think it's pin A4. So let's take a look at what my main loop is doing. Remember, this is 100 repetitions, high, low, high, low, high, low, and then after 100 times it should introduce an extra 2 cycles and go back to the start of that 100 repetitions. Every single shot, we can see that each high and each low is taking around about 25-30 nanoseconds. At a clock speed of 72 megahertz, we're looking at about 14 nanoseconds per cycle. So we're seeing that this is taking 2 cycles to make the GPI go high and then 2 cycles to make it go low. And if we manage to catch it at the appropriate time, we'd see that every time in 100, the low period will actually be 4 cycles long rather than 2 cycles long. This is running from flash, not from RAM. And because the assembly loop is or assembly code is very simple and sequential, at least for the 100 repetitions, the prefetch buffer within the STM32 is able to avoid any impact of having the 2 wait states configured, which is required for this frequency. Let's switch this device over now and run from RAM instead of from flash. Now, by default, I assumed that running from RAM, because of the wait states with flash at higher speeds, would be faster. Let's see if that's the case. We'll set the define to run it from RAM. We're running it. Let's take a shot. Oh, well, that's a bit strange. We're seeing it taking 40, 50 odd nanoseconds. It's staying high for 50 odd nanoseconds before it's going low. Still no low for 30 nanoseconds, but that's a little bit odd. So if we're seeing 55 maybe, then how many clock cycles is that? So I make that 4 clock cycles high and 2 clock cycles low. Just try it again. So this time we see short high, short low. That looks good. So we're seeing a lot more inconsistency. And we can see on that one, it looks like maybe it's 4 cycles high, 4 cycles low. We're seeing a lot more inconsistency in the behavior of the code because it's running from RAM. And I think what's happening here is, despite the fact that it should be just as fast to get the instructions into the CPU, there's contention on the bus. The bus is not just being used to pull instructions to the CPU, but I'm also writing to the GPIO to make it go high and low. And that means that sometimes when it's trying to pull instructions in, it has to wait for that. Actually, we've introduced some weights when running from RAM, and we'll just confirm, just go back to the running from flash case and check that we are seeing the behavior that we thought we were seeing. There we go. 2 cycles high, 2 cycles low. 2 cycles high, 2 cycles low. 2 high, 2 low. So every 1 time in 100, I'd expect to see low for 4 cycles, but we're seeing much better performance out of this STM32 running the code from flash, despite the fact we have the weight states configured. Now, your mileage is going to vary, particularly if you have more branching, more complicated assembly code that you're trying to execute. In fact, the use case that I have in mind for the STM32 has a more complicated main loop with a bit of branching in it, and it runs substantially slower than this from flash. And actually, I think in that case it tends to run a little bit faster from RAM, but it's more inconsistent for RAM, I think for the same reasons, because I'm performing GPIO operations. I'm therefore having to write to those registers, and that's creating bus contention. I hope you enjoyed this whistle-stop tour of bare metal programming the STM32F103 and configuring the various clock sources and squeezing out the last possible kilohertz from the internal oscillator on the device. I hope you also enjoyed the comparison between the STM32 and the FCM32 Chinese clone. If you're interested in trying this out for yourself, I'll put the link to the GitHub repository with the code in the description. If you've got any questions or any corrections you want to make, please put those down in the comments. If you enjoyed the video, please do stick around for the next one. Till next time, rock on.